Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the lecture 8 of this course. Let me just quickly revise what we did in the last lecture. So we were discussing about thrust required for a level unaccelerated flight. The thrust required was Tr equals to W by L by D. L by D was the aerodynamic efficiency, and we discussed what is the thrust required minimum, what should be the minimum thrust required to fly at level flight, that is T thrust equals to drag and L equals to W. And then we had a look at the graphical approach of finding the curve between thrust required and velocity. Alright, so let us quickly review or see the graph that we had plotted in the previous class. Alright, so this was the curve, that is thrust required with the velocity over here. Alright, thrust required with velocity over here. This is the thrust required minimum, for which the velocity will be at thrust required minimum, or velocity at which L by D is maximum. Alright, so now let me ask you one question here. So in this, we'll get to know how this curve is actually behaving, why the curve is behaving like this. We'll be discussing that today. And let me ask you the question over here, how alpha is actually varying in this curve. Okay, so think in this way, how angle of attack is changing. Alright, so let me answer that question for you. So today is this is lecture number 8. So how alpha is varying in this graph? Alright, remember CL versus alpha curve, CL versus alpha for the cambered airfoil, it was something like this. Now as alpha increases, so because of this curve, there will be change in CL, in fact increase in CL. Alright, so as alpha is increasing, there is increasing CL. Now for maintaining lift equals to weight, we know this equation, CL equals to 2W by rho s V square. Okay, now W is constant, area is constant, assuming we are flying at the constant altitude where density is also constant. Alright, so now at particular altitude, density is constant, W is constant, area is constant. So now as V is increasing, so to maintain lift equals to W, lift equals to weight. Alright, so this equation was for lift equals to weight. Alright, so to maintain lift equals to weight, CL has to what? If this velocity is increasing, to maintain this equation, so CL has to decrease. Alright, now when CL is decreasing, then what is happening to alpha? Then alpha will also have to decrease. Okay, so now as velocity increases, CL is actually decreasing, and so alpha is also decreasing. Alright, opposite is true. When velocity is increasing, CL has to increase, and so alpha has to increase. Alright, so you can mention in the curve here in the previous figure, here we have increasing alpha in this direction. Okay, or in this direction is decreasing alpha. Alright, I hope it is clear. In this direction it is decreasing alpha, since velocity is increasing and CL has to drop, and since CL has to drop, the alpha will also have be reducing. Okay, and opposite it's true for in this direction, when velocity is reducing, alpha has to increase, that means CL has to increase. Alright, so please keep these things in mind, but also please note, at higher velocity, as the velocity is decreasing, as the velocity is decreasing in this direction, thrust required also decreases. It becomes minimum at this point. It becomes minimum at this point, but again at lower velocities, then thrust required again increases. Okay, so thrust required is again increasing over here. So what is happening over here? Okay, that is the question that we need to address. All right, so let me repeat here. As the velocity is reduced, the thrust requirement also reduces. It becomes minimum, but beyond a certain threshold, if velocity is reduced further, then the thrust requirement increases. Okay, so we are interested to know what is happening in this plot. Okay, so let us address this question. Okay, so now we know that thrust required is equals to drag. Okay, QS CD over here. Now what is CD? CD is equals to CD naught plus KCL square. Okay, so now thrust required we can easily write here QS CD is nothing but CD naught plus KCL square. Opening the brackets, QS CD naught plus QS KCL square. Now for lift equals to weight, what lift equals to weight, we know CL is given as W by QS. Okay, now we'll substitute this CL in this equation. So finally we get TR equals to QS CD naught plus QS K into this whole square. Okay, so this will be W by QS whole square. So this becomes QS CD naught plus, so this one QS and this one QS vanishes. So we have K W square upon QS. Alright, so remember what was dynamic pressure? Q equals to half rho V square. So let us write in terms of the velocity. Alright, so thrust required equals to half rho V square S CD naught plus 2 kW square by rho V square S. Okay, 2 I have taken to the numerator. Alright, now remember this equation that we have just written, CD equals to CD naught plus KCL square, right? What was this KCL square? This was induced drag or drag due to lift. What was this? This was parasite drag or zero lift drag. This was zero lift drag. Alright, so likewise this will be actually zero lift thrust required. This is zero lift thrust required and this is lift induced thrust required. Lift induced thrust required. Okay, this is zero lift thrust required, this is zero, then this is lift induced thrust required. Now look at the velocity over here. Here we have velocity in the numerator, that is square of velocity, and here we have velocity in the denominator. Okay, so at higher velocities, zero lift, this term will actually dominate. Okay, so at higher velocities this term will actually dominate, that is zero lift thrust required will be dominating. This will be very high, but at lower velocities this will be dominating. That means lift induced thrust required will be dominating. Okay, so that is what I will try to plot the figure here, that is thrust required with velocity. Okay, thrust required with velocity. So let me plot first of all 0 lift thrust required. This is 0 lift thrust required. It becomes dominant at higher velocities. Okay, so at lower velocities it is very low. So this is 0 lift thrust required. Alright. What about lift induced thrust required? So it will be dominant at lower velocities. Alright. It will be dominant at lower velocity. So this will be high at lower velocity. So this is lift induced thrust required. Alright. Now the total effect of these two will be the net thrust required. Okay. So this is the net thrust required. Alright. So this is how, remember, we plotted the curve between thrust required with velocity. Right? We plotted the curve between thrust required with velocity, and this is actually the net lift thrust required. Net lift thrust required curve. Okay, net lift thrust required curve. Now this is the point at which the thrust required is minimum. Alright, and this is the velocity at which we have thrust required is minimum, or L by D is maximum. Remember, velocity at which thrust required is minimum, or velocity at which L by D is maximum. Now if you have to tell the pilot that please fly at thrust required minimum, then will the pilot understand? No, right? So we need to tell in a language that pilot can easily comprehend that what we are talking about. Okay, so we need to tell the pilot that please fly at this velocity so that thrust required is minimum. Alright, now what is the velocity that is required to fly at thrust required minimum? Velocity to fly at thrust required minimum. What is the velocity to fly at thrust required minimum? Now we need to find that velocity. That means I am talking about this velocity. Okay, and this is the velocity at which thrust required is minimum, or velocity at which L by D is maximum. Okay, so now we will be finding this velocity. Okay, now we have already written an equation. We will be differentiating equation number 3. Let me write the equation number. So this is half rho v square s c d naught plus 2k w square rho v square s. Okay, so this is equation number 3. Alright, now we will be writing this equation first of all in terms of q. Writing equation 3 in terms of q. Why am I writing in terms of q? Actually it becomes easier to do the differentiation of this equation. Okay, so first of all let me write this: thrust required equals to q s c d naught plus kw square by qs. Okay, it becomes easier to do the differentiation. Now if let me write this dtr by dq. dtr by dq is what? So dtr by dv into dv by dq. Alright, so now we'll be doing the differentiation of this equation number 4. With respect to q and equating to 0. Remember calculus, for finding any minimum point we need to do the differentiation of this curve and then equate to 0 to find the minimum or maximum points. Alright, So now let us find dtr by dq. So dtr by dq is, here we have only one q over here, so this becomes s cd naught. Here we have q in the denominator. All right, so how do that you do the differentiation when x is in denominator? So minus 1 upon x square, right? So s cd naught minus k w square upon q square s equals to 0. So you can write here s cd naught k w square upon q square s. So cd naught equals to k w by qs whole square. So this s I have brought it here and it written in the whole square form. Now remember what was w by qs for lift equals to weight? Yes, it was equals to cl. Cl equals to w upon qs. All right. So I can write here k cl square. So cd naught becomes k cl square. All right. Now the equation was cd equals to cd naught plus kcl square. What was this kcl square? That was induced drag, that is cdi. Remember, cd naught equals to cdi. This was induced drag and this is zero lift drag. Okay. So now here we have cd naught equals to this cd naught equals to kcl square. This kcl square is nothing but induced drag, that is cdi. Okay, so that means zero lift drag is exactly equals to drag due to lift. All right. So now cd naught equals to, can mention cd naught equals to, what is cdi? Cdi is kcl square. Okay. So now you can find what is cl over here. Cl is square root of cd naught upon k. So once you have cl, we can easily find velocity corresponding to this cl. Okay, so velocity is given as 2w by rho s cl. Okay, so this is a square root. See, everything is coming from this equation only. Okay, so please do not forget this equation, 2w by rho s v square. Okay, so v equals to 2w by rho s cl. All right, now this is the velocity for which thrust required is minimum. Okay, so 2w by rho s, what is cl? Cl is cd naught by k. All right, so this is the velocity at which thrust required is minimum, or the velocity at which L by D is maximum. All right, so now we are able to tell pilot that to fly at thrust required minimum, please fly at this velocity, that is velocity at which thrust required is minimum. All right, so now we'll be doing an example and we'll also be simulating in MATLAB as well. Now consider a jet powered executive aircraft all right, so here with this, let me show you first of all the aircraft example that I am considering. So This is the aircraft that I am considering for this example. This is a jet powered executive aircraft. Alright. This is considered from the J.D. Anderson book, chapter number 6. So the wingspan B equals to 16.25 meters, wing area 29.54 meters square, normal gross weight So please make a note of these parameters. So this aircraft example I will be considering again and again for various concepts in aircraft performance. So please make a note of these aircraft parameters. This will be used again and again in this course. The normal gross weight is 88,176.75 newtons. Here we have two turbofan engines. Which is producing 16,242.5 Newton thrust each at sea level. Okay, this is producing this much thrust at sea level. Alright, parasite drag CD naught is also given. Parasite drag coefficient CD naught equals to 0.02. Oswald efficiency factor. I am writing the names so that you are well aware of these terminologies. Oswald efficiency factor. What was Oswald efficiency factor? Denoted by small e equals to 0.81. Alright. Next, what is given is the fuel capacity. So please note, in every example I will be considering these details. I will not be writing again and again. The fuel capacity is 1119 gallons of kerosene. Alright. Next we have thrust specific fuel consumption. Please do not be afraid from these terms. This I will be explaining in the coming lectures. Thrust specific fuel consumption. This is denoted by CT. Since it's a jet engine, I am denoting it by CT equals to 1.667 10 to the power of minus 4 per second. How we are getting these units per second? This we will be discussing in due course of time. Alright. Now the question is plot thrust required. Plot thrust required curve with velocity. Okay. Plot thrust required curve with the velocity. Now let me solve here also, then we'll be going to MATLAB for plotting the curve. Now what was the procedure in the graphical procedure? It started with selecting one particular velocity. Remember? So select particular velocity. Say for this example, I'll consider 50 meters per second. Okay. So after selecting the velocity, we have chosen the velocity. Then we find the lift coefficient. CL equals to 2W by rho V square S. 2W by rho SV square. Then we find drag coefficient CD. Then we find CL by CD. And then finally we get it. Thrust required TR equals to W by CL by CD. Okay. Okay. So now let us find CL. Our first step is done. Second step is CL equals to 2W by rho v square s. This is for study level flight, please remember. So this equals to 2 into 88176.75 divided by density. If it is not given, always we know at sea level it is 1.225. Velocity we consider 50 meters per second into 29.54, which is the area. Now here, is the dimension correct? In one of the classes I have discussed about units. Alright. So here weight is already given in newtons. Okay. Had it been given in kilogram, you have to convert it to newtons. Otherwise, you will not get CL as a dimensionless number. Alright. So this should be in newtons. This is kilogram per meter cube. Perfectly fine. This is velocity meters per second. Then this is the area in meter square, which is okay. Now if you calculate this, you approximately, I am writing only approximate values. Alright. So this is 1.9493. Now we are done with the second point. Third point is finding CD. CD was CD naught plus K CL square. Okay. So here CD naught is given to us. You have to just find K. K equals to 1 by pi EAR. Okay. Even aspect ratio you have to find. Aspect ratio equals to B square upon S. This comes out to be 8.9391. Okay. And if you substitute K equals to 1 upon pi, E was given as 0.81. Aspect ratio is 8.9391. So K is approximately 0.0439. So finally we can calculate CD value. CD equals to CD naught plus KCL square. CD naught is 0.02 plus 0.0439. CL we already calculated, 1.9493 whole square. So CD approximately will get 0.1868. Okay. Next is finding CL by CD. So 1.9493 divided by 0.1868. So this comes out to be 10.4352. Okay, I am writing the approximate values. Finally, we can get thrust required. Thrust required equals to W by CL by CD. Okay, W was also given to us, 88,176.75 divided by CL by CD, 10.4352, and thrust required comes out to be approximately 8449.9338 newtons. So approximately 8,450 newtons of thrust is required if you want to fly at velocity of 50 meters per second at sea level. Alright, so this actually we got it for one velocity, right? For example, we plotted it for one velocity V, CL, CD, CL by CD, and then we have thrust required. So this we did for 50 meters per second. CL requirement was 1.9493. 0.1868 was the drag coefficient. CL by CD was 10.4352 and thrust required was 8449.9338, which is in newtons. Alright, so similarly we can select other velocities, okay, and you can easily plot between velocity and thrust required. So this becomes quite tedious if we do it manually again and again. So let us use MATLAB for this. Okay, so now let us quickly switch to MATLAB. This is the MATLAB window as I have explained multiple times. So let me begin the code from here. CLC, clear, close all. Alright, close all will close all the figures. Clear will clear this workspace over here on the right hand side. And CLC will clear the command window. Alright, so you can see here in the workspace already there are parameters. Let me run this. I have saved this file as tr_curve.m. Let me run this. So now we have cleared the command window as well as workspace. Alright, and if there were any open figures, that will also be closed. Now let me write the given values first. So here weight is equals to 88,176.75. Okay, so this is the weight in newtons. Weight in newtons. Next, span B equals to 16.25. So wingspan in meters. I am writing this because I will be using this again and again. Wingspan in meters. Then sea level density, rho equals to 1.225. Air density, it is kilogram per meter cube. Fine. Then what else is given? Area, S equals to 29.54. 29.54, this is the wing area. Let me give some space over here that it looks better. Alright. Okay. Next is parasite drag coefficient CD naught, which is 0.02. Zero lift drag coefficient. Okay. Zero lift drag coefficient. Next is the Oswald efficiency factor, E equals to 0.81. Next is aspect ratio. Let me denote it by AR equals to B square upon S. So B we have already defined. So B square upon S. Okay, so this is the aspect ratio. Then we find the induced drag correction factor, capital K, equals to 1 upon pi E AR. So whatever is in the denominator, always mention in the brackets. Otherwise, MATLAB will assume it is in the numerator. Okay, pi into E into AR. Okay, now this is your induced drag correction factor. Okay, now we need to create a velocity vector. Okay, velocity vector. in meters per second. V equals to, let me define here, LINSPACE, lin space. Let me consider velocity from 50 to 300 meters per second. Okay. And divide it into intervals, say 200. You want to see what is actually happening? So let me save this and let me run this code. Now see here, so these are the parameters that we have defined until now: aspect ratio, B, CD naught, and so on and so forth. So these all are scalars, but the velocity here is a vector. If I double click this, so velocity starting from 50 meters per second, then 51, 52.51, and so on and so forth. Alright, so it is going till 200 iterations, or it's a vector. Okay, it is going till 350 to 300 meters per second. Alright, that is what we have created over here, a vector of velocity. Now that we have velocity, now calculate CL for each velocity. Okay. Now remember, velocity is a vector. What we have to do here, we have to write here element to element multiplication, otherwise MATLAB will throw an error. So in one of the classes I have already told this. Alright, so 2 into W. So instead of writing only divided by, we'll write dot divided by, again brackets, rho dot into, okay, just dot in front of the operator. Alright, so V square, again dot square. Okay, since this is a vector. Alright, then into S, again dot into S. Alright, now let us see what did we do here. Now if I run this code, so now see, now CL also is a vector. Okay, so it has calculated the value of CL at various velocities. Alright, then let us see what did we do in our calculations. And we took the velocity of 50 meters per second, right? So in 50 meters per second, the CL was around 1.94. Okay, so here it is 1.94. Okay, fine. So after CL, we want CD. Calculate CD using drag polar. Okay, so now CD is equals to CD naught. CD naught we have already mentioned, K we calculated, into CL square. CL square. Okay, now here again CD will also be a vector since CL is a vector. Okay, so you have to write here CL dot square. Alright, CD CL dot square. If I run this, let me see if there is any error. No. So CD is also a vector over here. Okay. Then immediately what do? We can find thrust required. So I'm just skipping the step that CD over CL, that we can rightly do it, include it in thrust required. So we can calculate thrust required. Calculate thrust required. Okay, so TR equals to W, it was W into CD by CL. Okay, so now this is a vector. I am again writing dot into CD divided by, again dot divided by CL. Okay, now thrust required will also be obviously a vector. Fine. Okay, Now let us plot the curve, that is plot TR versus velocity. Percentile plot TR versus velocity curve. Okay. Now for that we have a simple command, plot. In x-axis what do we have? Velocity. Okay. In y-axis we have thrust required. Okay. So it should be in red color, for example, and the line width, it is throwing an error since I have not put quotes over here. Okay. The line width equals to line width comma 1.5. 1.5. Alright. So here I can include it. So V comma TR comma, okay, so here should be comma, right? Now it's fine. So V comma TR, fine. Okay. In X label, we can mention, what do you want to write in the x-axis? Obviously it is the velocity in meters per second. Y label, in Y label we have thrust required in newtons. X label, Y label, we can also add a title of the plot. Alright, let us write thrust required versus velocity. Okay, let us keep grid also on and put a limit in the x-axis. X limit, I want limit should go from 0 to 300. This is actually a vector. I have to write in a square bracket 0 to 300. Okay, so all looks good as of now. Let us see if there are any errors. Let me pull this down. Okay, let me save this, and now let us run this code and see if everything is running well. Yeah, so here is the thrust required plot with respect to velocity. All right, so I've given the x-axis limit from 0 to 300. I'm seeing over 300, and the velocity started from 50 meters per second. It is going up to 300 meters per second. All right, and what is the thrust required at 50 meters per second? It is coming about to be 8,141. Okay, if it is around 50 meters per second, 8,461. Okay, so we calculated nearby this value. So this is the exact 8,460 newtons of thrust is required if you would like to fly at 50 meters per second. Now let us check what is the thrust required to fly, at minimum thrust required. The minimum thrust required, I am just hovering over here to see what is the minimum thrust required. So 5237. 5248. Okay, so hovering around 80 meters per second. Okay, it is hovering around 80 meters per second. So now let us check. Let me go to this. So we can also find the velocity at which thrust required is minimum. Remember, I have drawn this. We have found the relation for thrust required minimum. What is the velocity at which the thrust required is minimum? This was the expression. Velocity at which thrust required is minimum, 2w by rho s CL. CL is square root of 3d naught upon k. Now let us find manually as well what is the velocity at which thrust required is minimum. from plot anyhow we are able to see it is approximately around near 80 around 80 meters per second. Okay, fine. Let me write here velocity at which thrust required is minimum. All right, now let me write here velocity underscore tr minimum so that it makes sense, equals to we have square root sqrt. Okay, then again in the numerator we have 2 into rho, 2 into rho into square root sqrt k upon cd naught, k upon cd naught into w by s into w by s again in the bracket. So this is the same expression I am writing over here. Okay, the one that I have just shown you. So this is square root of 2 into rho to square root of k by cd naught into w by s. All right, now let us see what is the velocity at which thrust required is minimum. I am running this code. It is showing us the plot. Let me go to the workspace. All right, so this is the expression that I have written over here, velocity at which thrust required is minimum. So this is coming out to be velocity at which thrust required minimum is 85.0019. Okay, so it is saying at this velocity your thrust required is minimum. Now let us go to the plot once again and check at 85 meters per second. So at 82 it is 5237, 5230, so 5229. Okay, so at this velocity we have thrust required is minimum. So we can also find using this manual calculation as well, or you can see from the plots as well. All right, now let us proceed further. Let us proceed further with our understanding on the thrust required minimum. All right, so we have discussed the graphical approach as of now. Now let us proceed with the analytical approach, how you can find the thrust required minimum, what is the condition for thrust required minimum, and what is the velocity at which the thrust required is minimum. Okay, now let me go ahead and write over here analytical approach. Okay, now I'm rewriting equation 4 as, so this was the equation 4, thrust required, yeah, thrust equation number 4, thrust required equals to q as cd naught plus kw square upon qs. This was equation 4. Now let me write here ks thrust required equals to qs cd naught plus ks by q, ks by q w by s whole square. Thrust required equals to qs cd naught plus ks by q w by s whole square. So this equation is same actually, and we can write here q into tr equals to q square. I'm just taking the LCM here, so q square s into cd naught plus ks into w by s whole square. So now I can write here q square s cd naught minus q into tr plus ks W by S whole square equals to 0. Now this is the quadratic equation, right? This is actually a quadratic equation. We can easily find, we will get two values of Q. Okay, so let us go ahead and find the two values of Q. Q equals to, the denominator will be having 2 into S CD naught, that is 2 into A. Okay, and here we'll be having minus B plus or minus square root of B square minus 4AC. Okay, so here we'll be having minus B, so this will be thrust required, plus minus square root of B square minus 4AC, thrust required square, minus 4S CD naught to KS W by S whole square. Okay, so you must be making notes of this, and let us proceed further. Let us write this equation. Q equals to, let me take here it as 2 CD naught, so TR by S plus or minus 1 by S square root of TR square minus 4 into S square CD naught K into W by S whole square. Okay, fine. So this equation can again further be written as TR by S plus or minus 1 by S square root of TR square minus 4 into S square CD naught K W by S whole square divided by 2 CD naught. Okay, so this is the same equation that I mentioned over here. So here TR by S is actually thrust loading. Okay, but generally we do not use, this is having of little significance. So we will not be using much of this TR by S. So instead of TR by S, what makes sense is T by W. How much thrust is required to lift this weight classification of the aircraft. So TR by W. So let me write in terms of TR by W. So that is Q equals to TR by W to W by S. So both equations will be same. Okay, do not worry. Plus or minus TR by W so here in this case 1 by S. Okay, so TR by S whole square. 1 second. Okay, so TR by S plus or minus, this will be TR by S whole square. This is whole square over here, please make a note of it. TR by S whole square minus 4 CD naught K, 4 CD naught K W by S whole square. We can remove S square from here. Alright, so please make a note of it. Alright, so TR by W into W by S plus or minus, so we have TR by W whole square. Here we have W by S whole square minus 4 CD naught K W by S whole square divided by 2 CD naught. So this is a little bit lengthy derivation. Please bear with me. We'll get to the results quickly. Now let us substitute Q equals to half rho V square. So we have half rho V square equals to TR by W, W by S. Let me write here TR by W, W by S plus or minus. Let me take W by S common from this equation. TR by W whole square minus 4 CD naught K by 2 CD naught. Okay, now this can be further written as in terms of velocity. Just so this gets cancelled, 2 and 2 I will bring rho here in the denominator. So velocity is written as dr by w, w by s plus or minus w by s square root of dr by w whole square minus 4 CD naught k divided by rho to CD naught. So here we had v square, so we'll write this whole term 1 upon 2. So let us take this as equation number 5. So this equation 5 is actually giving us two velocities. We have plus or minus over there, right? It's giving us two velocity with a given value of dr. With a given value of thrust required. Okay, so here velocity depends upon, if you see this figure equation carefully, this velocity is depending upon dr by w, w by s and CD naught and k. So that means it is depending upon this dr by w, we call it as thrust to weight ratio. Second is wing loading. W by S is called as wing loading. Now what are these terms? Third is of course the drag puller. Okay. So remember thrust required versus velocity. This is thrust required versus velocity. This is the curve. So for example, as we have seen here, it is giving two velocities. So one thrust required is corresponding to actually this velocity as well as this velocity. Okay, and this is of course thrust required minimum. Okay, velocity at which the thrust required is minimum. So this equation is giving us two velocities because of the quadratic equation. So one thrust required will correspond to this point, and the same thrust required will also correspond to this point. All right. So now we will be discussing about thrust required, thrust loading, all right, wing loading, thrust to weight ratio in the coming classes. Okay, in the next lecture. All right. Thank you.